All right, so guys, let me lay out for you again what we're up to today. So you have this stuff, note-taking materials, you got periodic tables, you got calculators, okay, and you have at some level gotten rid of distractions, whatever that means to you, and you're ready to go. So guys, let me explain to you then what we're going to do today so that you are connecting with how this is all going to unfurl. So guys, 2 times ago, when I was gone, you learned how to calculate formula masses, right? It was this homework assignment. It took us about 11 seconds to grade because you guys all, I believe, felt really comfortable with this. For those of you that didn't do this assignment, remember last time I told you guys, you got to do this for today. If you have done it today, we can maybe talk at the end of class about getting your score recorded. If you're in Miss Call's class, you'll have to wait because she's not here. Sorry, that was for Miss Call's students. But guys, you're good on this, right? And then today, after last time, we now have a good sense of dimensional analysis and how that works. And guys, today, here's what we're going to do. We're going to begin the day by going back and calculating a formula mass. Then, guys, we're going to take this idea of formula mass and we're going to lift it out of the abstract and into the practical. And you're going to find out that formula mass calculations are a waste of time. That very first assignment that you did when you were calculating formula masses has no practical application whatsoever in the world. Those numbers are worthless. And we're going to talk about why they're worthless. And guys, it's going to be super critical that you understand why they're worthless. So if at that moment you don't understand why they're worthless, you got to go, hey, I don't get it. Because guys, then we're going to fix the problem. And fixing the problem is where you're going to have this magic moment and you're going to go, no way, that's pretty cool. Now guys, here's the risk. As we're fixing the problems, this is going to get a little childish. Not childish in terms of stupid, but childish in terms of playful. It's going to get a little, you'll see, it gets a little weird. Bear with me, because guys, at the end of childish is going to be, that's really cool, right? Then guys, after we do that, we're going to dig into the concept a little bit more. And at the end of that, you're going to understand the concept of the mole. Guys, once you understand the concept, then we're going to invite dimensional analysis into this, and we're going to start doing the math of the mole by using dimensional analysis. You guys ready to go? Here we go. So guys, do this on your paper just like it was 2 times ago's homework. Guys, calculate the formula mass for our good friend table salt. Now, gang, as you're working on this, please remember this is weird, but if you can show no work, that's better.
Where do we round to again?
Yeah, so right now, Chase, that's going to be really important. Right now, we're rounding to 1 decimal place. That will no longer be the case in about 20 minutes, but for now, we're going 1 decimal place. There's actually, and so if you Google this, if you're interested, just go on Google and Google high school chemistry mole activities. And you know what you're going to find? You're actually going to find patterns that you can put on top of felt and cut them out and make a little rodent, a mole. And so there are actually chemistry teachers that when they introduce this material, they have their classes have an arts and crafts day. Kind of like the
material when you were talking about
like your useless bird feeder.
it's like the bird feeder for high school students. So don't go there. But we are going to talk about that. Are you guys all done? You okay? Okay, so guys, remember that when I gave you the answers to the homework, I gave you stuff like this. And I gave you this because this is the thinking behind the answer. But guys, right now, you've got to be able to come up with 58.5 AMU, right, which is AMUs, which is atomic mass units. Guys, any problems with that? You guys all okay? You all arrived at that answer, right? And Chase got his thinking about this idea that right now we're rounding to 1 decimal place. That's not going to be true at the end of the day today, but for now we're going 1 decimal place. Any thoughts or concerns? Okay. Now, guys, let me explain to you why this number and all of these formula mass calculations are worthless to you. You ready? So we are going to go to lab next week. Actually, it's today Wednesday. We're also going to go into lab on Friday, but you'll see it's different. But next week we're going to go into lab, and we're actually going to start weighing out these chemicals and doing chemistry with them. So, guys, imagine this. Imagine that and guys, this is the important part. Don't miss this. Imagine that you go into lab and you're handed a weighing boat and you're handed a beaker of salt, and you walk up to the balance at the back of the room and you're asked to weigh out this much salt, right? You spend a ton of time coming up with this formula mass, and now you're asked to go into lab and weigh out this much salt. And so you put the weighing boat on the balance and you hit tare and you start doing this. And the question is, how much salt do you need for it to weigh that much? Then that's the problem. So guys, if you're not picking up on this, this is the idea. So guys, you understand that salt is typically in small crystalline chunks. So when we talk about 58.5 atomic mass units of salt, it's not a pinch. It's way less than that. It is also not a crystal. 1 small crystal of sodium chloride is way heavier than 58.5 atomic mass units of salt. So guys, the question then becomes, how much salt weighs 58.5 atomic mass units? And the answer can only come at the atomic level. Because guys, if this is a crystal of salt, this is 58.5 atomic mass units of salt, right? It's 1 atom of chlorine, 1 atom of sodium. Guys, that's how much salt we're talking about if we're talking about 58.5 atomic mass units of salt. And guys, obviously that number is worthless to it because we can't use those sorts of scales in lab. You get the idea? Okay, so guys, if this isn't making sense to you, don't write this down, but let me offer you this. So guys, how much is 58.5 atomic mass units of salt? Well guys, an atomic mass unit, you learned this back in September, is 1.67 times 10 to the negative 24th grams. Don't write that down. But doing the math, guys, this is it. When I told you to go into lab and weigh out 58.5 AMUs of salt, this is what it weighs in grams.
That's easy to calculate.
Right. So, again, if you're still not picking up on this, guys, the balances that you use in lab, which cost a couple $100, weigh out to 2 decimal places. The balances that we use in AP chemistry, which cost $5,000 each, weigh out to here. But guys, to weigh out to 58.5 AMUs of salt, guys, this is what we've got to be able to weigh, and that is physically impossible, meaning that all of these calculations were a waste of your time because we can't use them practically in lab. You see the problem? Are y'all? We're good. Now we're going to fix it. You ready? This is cool. Don't write any of this down, but check this out. Guys, this is good stuff. So this is where this is, uh-oh. What do I do? How do I move that? Did it move?
It's gonna blurp out.
It is going to blurp out. See? I love that you knew that. All right, there we go. So guys, this is about to get a little childish. This is about to get a little playful. But guys, what I'm going to do is I'm going to establish a principle with you. Don't write this down. I'm going to establish a principle for you that will actually lead us to the solution of the problem. So guys, let's again restate the problem. Why is the formula mass of salt of 0 value to us?
It's so
Okay, too small, right? So guys, the bottom line is we can't weigh this. We can't weigh 1 chlorine and 1 sodium. So guys, the question then becomes, how do we fix the problem? If we can't weigh one of these, what do we need to do? Get more, right? If we can't weigh 1 because it doesn't weigh enough, get more, and that will weigh more. Get the idea?
Yeah.
Okay, check this out. Again, you're not writing this down. So here's what we're saying. if we have 1 sodium chloride, right? That has a name. It's called 1. And guys, 1 sodium chloride is 58.5 atomic mass units, which is this many grams, and that does not weigh enough for us to weigh it. Good?
Yeah.
So what are we going to do? Well, we're going to get more. So guys, let's talk about more. So if 1, and this is going to be stupid, bear with me, but guys, if 1 doesn't weigh enough, what if we get 12? Will 12 weigh more than 1?
Yeah.
How many times more? 12 times more. But guys, why did I pick 12? And the answer is because 12 has a name. What do we call 12? A dozen, right? You guys are comfortable with this idea that groups can have names. So 12 is called a dozen. So, will 12 weigh more than 1? Yeah, 12 times more. I did the math. This will weigh 702 atomic mass units. How much does that weigh in grams? And guys, the answer is this. Can we weigh that?
No.
Still not enough. So now we need to get even more. So let's get really crazy and let's get a dozen. Huh? How much is a dozen? 144. So guys, 144, and this is childish, but thanks for bearing with me. Guys, 144 is going to weigh more, right? But what do there you go. So guys, do you guys, and maybe you don't know because you grew up in Utah. Guys, what do we call a dozen? Do any of you know? A dozen, no. So the reason I say not in Utah, because growing up in Wyoming, every kid in Wyoming knew what a dozen was, because in Wyoming, bottle rockets are legal, and every summer we would go buy dozens of bottle rockets and then shoot them at each other. It's a horrible idea. Don't do this. But, guys, we would go to the fireworks stands and we would say, I want a dozen bottle rockets, but you don't call them a dozen, you call them a gross. So guys, a dozen is actually called a gross. So if you go to a fireworks stand and say, I need a gross of bottle rockets, they will hand you 12 packages of 12, and that's a gross. You get the idea?
Yeah.
Chandler, are you with me?
Yep.
Here we go. So, guys, this is then going to weigh more. Don't miss this. How much more? This much more. But what does that weigh in grams? It weighs this, and that is still not enough. So guys, now we're done with childish. Ready? Don't miss this. So guys, what we've established is this. If we can't weigh 1, we need more. But we're also learning that we need a lot more, because 12 or 144 is nowhere near enough. But we also now are comfortable with the idea that groups have names. 12 is a dozen, 144 is a gross. Good?
Yes.
Now watch this. Here's the question. Guys, how many sodium chlorides do we need to finally have enough that there's enough that we can weigh it on our balances? Guys, then there's an answer to this question, and this is magical. Guys, check this out. The answer to this question is 602 septillion. That is how many sodium chlorides you need. Guys, don't look away. This is how many sodium chlorides you need in order to have enough to weigh them. But guys, just like 12 is a dozen, 602 septillion also has a group name. It's called a mole. Okay? Now guys, don't overthink this. Ready? If you have a dozen eggs, how many do you have? 12. If you have a mole of eggs, how many do you have? 602 septillion. It's just a counting group. Don't overthink this. Guys, a mole is just, it's a big counting group, but it's just a counting group. Now guys, watch. Ready? This is cool. So, 12 weighs more, 144 weighs more, 602 septillion is gonna weigh more. Guys, the question is, how much more? You ready? This much more.
Oh.
Wait.
Go ahead. It works with so here. Isn't that amazing? So the guy that did this, his name is Avogadro. And you're going to find out in April, he was actually studying gases. And what he was trying to do was figure out a way to weigh and count gas particles. And as a part of that research, he actually figured out how to take these numbers on the periodic table and convert them. And this is what we're doing. Convert them from AMUs to grams. And he figured out the number of things that need to be in a pile so that that pile's mass in grams is the same as one of them is in AMUs. Isn't that brilliant? Yeah, that's super smart stuff.
Half the time we won't even have to do the calculation of 58.5 times.
Exactly, you're done. You're exactly. So, guys, this now means that all of these calculations that you did when you figured out formula mass now are meaningful to us. All we have to do is change the AMUs to grams, and now we're working in moles rather than individual particles. Huh? That's pretty good stuff. Now, guys, please.
Are there scales that can measure AMUs?
Sort of. We're getting closer. Well, yes.
Wouldn't that have to be like?
Yeah, they don't work like the scales that you're. So the bottom. So do you remember what is an AMU? It's the mass of what? A proton. And so we actually can weigh protons.
It's not by setting it up.
No, it doesn't look anything like a balance. No, it's there. It's the science behind it is really cool. But we can weigh protons. So, guys, let's dig into this number. Grace got us thinking about, how did they come up with this? Well, guys, and this you need to start writing down. Let's dig into this number, a mole. So, guys, what is a mole? Well, it is simply a counting group like a dozen or a gross. Do not overthink this. It is just a counting group. But guys, this counting group is, forgive me, but magical because it allows us to convert directly from AMUs to grams. So, how many things are in a mole? And the answer is Avogadro's number. So guys, Avogadro's number is the number of things in a mole. It is equivalent in scientific notation to 6.02 times 10 to the 23rd. And guys, that is not exact. That is only 3 significant digits. Written out, it looks like this, and you don't need to do that. But guys, that is the magic of this number that allows us to convert right from AMUs to grams. I told you you'd like this. Some of you are sitting there going, no, I would have much rather just been playing on my phone.
Who names their child Avogadro?
That's his last name.
Oh, okay.
Yeah, no.
I was going to say, you carry a child for 9 months and name him Avogadro. Sounds like avocado. Avocado.
Not only are you guys bright and inquisitive, you're also very easily distracted. They probably do. Okay. So, guys, what I want to do before I dig into this with you more is we need to put this number in context. To varying degrees in this room, you're starting to appreciate what this number is all about. But guys, universally, the thing that you can't do is appreciate how big this number is. Guys, when you start trying to conceptualize how big is 602 septillion, you're going to quickly find that you've got to really stretch in order to get there. So guys, what I'd like to do is I'd like to help you stretch. Please don't write any of this down. Just become appreciative of how weird this number really is. So guys, here's the question. Don't write this down, just watch. Here's the question. How big is this number 602 septillion? Well, you ready? Here's an example. Right now, faster computers, not like the things we use to predict the weather, not Watson, but guys like my laptop, which is a pretty capable machine, can do about 8 billion things a second. Now what that means is if there are about 8, 9, is it 10 billion? Didn't we hit 10 billion people on the planet? I believe that's the case. But guys, if there are 10 billion people on the planet, My computer can count everybody on the planet in about a second. Wrap your head around that. 8 billion things a second. My laptop could count everybody on the planet in a little more than a second. Here's the question. How long would it take my computer to count to Avogadro's number? 602 septillion. What do you think? A couple hours? Day, year? 5 years? Guys, 2.4 million years. Every moment of every second of every day, 2.4 million years to count to Avogadro's number. Now the problem is this. You guys have a hard time thinking about tomorrow, right? That's a stretch for you. 2.4 million years is unfathomable. So now we've got to make this more realistic and a little whimsical. So guys, what if you have a mole of raindrops?
Dude,
Huh?
bless you.
So guys, if you have a mole of raindrops, don't miss this. How many do you have? 602 septillion. If you have a mole of raindrops, you have 602 septillion raindrops. Here's the question. How big of a bucket does it take to hold a mole of raindrops? As big as this. You're starting to realize it's going to get weird. So guys, I did the math. So what I did is I imagined that I had a cylindrical tank 100 feet across. So this room is about 30 feet wide. So imagine my room and the lab and Miss Call's lab. That's about 100 feet. Okay? Here's the question. How high would the walls have to be to hold a mole of raindrops? Ready? It would actually go to the sun and back 280 times.
Oh, it's not that big.
Thank you, Jeff, for ruining the analogy.
So what if you got a mole of like the animal?
Ah. So, guys, again, a little abstract because none of you have been to the sun. So then I said, what if we do something that might be more contextual for us? So, guys, what if we add a mole of airsoft pellets? So I picked airsoft pellets because I actually have some.
Wait, so like after school, I have that same bucket?
This actually used to be my solution to students that were tardy.
Does the gun just drop down from the ceiling? Like,
Jeff, you were one step away from this.
What'd you do?
I actually have thought about it. I was really close. So, guys, here's the question. Don't miss the significance because, again, this gets a little abstract. So, guys, what if you have a mole of airsoft pellets? How many do you have? Good. Okay, so here's the question. How big of a container does it take to hold a mole of airsoft pellets? So let's start slow. Would it fill my sink?
yeah.
Sure. Would it fill the room?
Yeah.
Now, guys, hold on. You say that flippantly, but picture that. This room full of airsoft pellets.
Yeah.
Yeah. What about the field house?
Yeah.
Picture the field house, guys. You can't picture, but picture the field house full of airsoft pellets.
Like
It's like a ball
what
pit, but
compression are we talking
Yeah.
about here? Like it's so compressed you can't move?
No. So just
Can you swim through them?
just like this.
Like trying to walk through it, like,
Just, I mean, I don't know if you could walk through it. I would suspect not because of the weight, but just like this. So, guys, the field house is not even close.
is it the
And when I did the math, things got weird, so I had to try to bring it back to something that we might be able to share. But it still got weird. So this is what I came up with from the math. In order to house a mole of airsoft pellets, you would have to turn the state of Utah into a Tupperware container. Flatten the entire state of Utah from Idaho to Nevada to Arizona to Colorado. Take the whole state and turn it into a Tupperware container. And guys, at that point, a mole of BBs would bury the state 253 feet deep.
Oh my God.
The whole state.
Dude, that drive is so long.
So guys, again, crazy. It's a lot, but it's still abstract. So allow me then to bring this back into the world of chemistry. Now guys, answer this question for me. What does a mole of seconds, what does a mole of raindrops, and what does a mole of BBs all have in common?
There's all this
The
long.
same number of things. Just like if you had a dozen donuts or a dozen eggs, what do they have in common? The same number of things. Guys, the same number of things. Now let's do one more. What if we had a mole of carbon atoms? How many do we have? 602 septillion. Guys, the question then becomes, how big would that be? And the answer is this. Guys, this is a mole of carbon atoms. How do I know? Did I count them? No, it would take my computer 2.4 million years. But guys, what about this? If these carbon atoms were the size of airsoft pellets, then this sample would expand to the size of Utah, 253 feet deep. That's how small atoms are. But how did I figure out that this is a mole of carbon? I weighed it. I looked up on the periodic table, and I found out the mass of carbon is 12 grams per mole. And this is a mole of carbon atoms. You get the idea? How many are in here? 602 septillion. So guys, can we all then agree on this idea? Don't write this down. If one carbon atom weighs 12 AMUs, then 1 mole of carbon atoms weighs 12 grams, and it contains 602 septillion carbon atoms. Do you agree? Now guys, watch this. Again, you're not writing this down. If this is true, then guys, let me extend with you a little bit. Now let's talk about 2 moles.
Oh boy.
So guys, here is 2 moles of carbon. What does this weigh? 24 grams. So guys, the mass of this is 24. The mass of this is 24 grams. How did I know? If 1 mole weighs 12, 2 moles weighs twice that, right? So it's just 2 times 12. Now guys, what about this? How many carbon atoms are in here? 2 times. So guys, if you have 2 dozen donuts, how many do you have? 24, 2 times 12. Guys, if you've got 2 moles of carbon atoms, you've got twice the number of carbon atoms in 1 mole, which is 602 septillion. So guys, the answer is actually 12.04 times 10 to the 23rd, which is just 2 times Avogadro's number.
What is that? Like
An
like
octillion, 20 septillion.
I'm not septillion?
Yeah, it's not important. So, guys, this then becomes the idea. Without knowing it, don't miss this transition. Guys, what we did is we established a relationship between moles and mass and numbers of things. And then we used those relationships to extend this into multiples of moles. Guys, without knowing it, you just did dimensional analysis. Let me say that again. Without knowing it, we just did dimensional analysis. Guys, all the math that we are going to do for the rest of the year relative to this is represented on this screen. The problem is it's not typically this simple, and therefore we need structure. This is the structure. Guys, write this down in your notes. Here's what you're going to do. Make each one of these boxes about 1.5 inches wide and 3 lines tall. Put one on the far right, one on the far left, one in the middle, and then connect them with lines. Make it as wide as your page. Now guys, do this. And if you're not sure what I mean, watch me with the board. Bring your units down. So in the middle, we have moles. Fill that box with moles. On the right, we have grams, which is mass, measured in grams. Then, gang, on the left, we have numbers of carbon atoms. We call those particles, And particles include atoms, molecules, and formula units. Now guys, this becomes the important part. How do we convert between them? And this is the tie to dimensional analysis. How do we convert between them? Well guys, look at what we did over here. We knew that we had 2 moles. We knew that that weighed 24 grams. The way that we knew that is we multiplied 12 times 2. Guys, where did 12 come from? The periodic table. 12 is the formula mass for carbon. So guys, right here, write this down. Formula mass is the conversion between mass and moles. Now guys, check this one out. On the other side, we figured out that there are this many atoms. Sorry, that's not true. There are this many atoms in 2 moles of carbon. Well, how did we know? Well, we multiplied 2 times the number of atoms in 1 mole. And guys, that number has a name. It's Avogadro's number. And that is the conversion between particles and moles. So guys, bottom line is this. All of the conversions that you are going to do for this entire unit will be found on this chart. All you're going to do is this. You're going to convert from moles to mass. In order to do that, you need to know the formula mass. Or you're going to go moles to particles, and in order to do that, all you need to know is Avogadro's number. So guys, this chart contains everything that you're going to do for this entire unit. We're going to do 2, and then you're going to work on your homework. You guys ready to go?
Yes.
Okay. So guys, you definitely want to write these down as examples. So it reads like this. What is the mass of 2.3 moles of sodium chloride? So guys, here's the question. What is this weigh? This is 2.3 moles of sodium chloride. What does this weigh? Now guys, stop. Here's the problem. Some of you are getting ahead of yourselves. We learned 6 steps to solve these problems. From having done the previous homework assignment, you should be very fluent in these. We set a goal, we pick a starting point, we draw a line, and we apply conversions. Guys, we are not going to abandon that structure because without it, we're going to get in a lot of trouble. So guys, step number 1 is set a goal. What are we solving for? What is the mass? And guys, our units for mass are grams. But guys, did you notice I didn't just write down grams? It's grams of NaCl. Some of you right now are thinking that's a waste of my time. That's fine if you make that choice. But understand, guys, next Thursday, you're done. Because what you're going to find out is the problems we're solving on Thursday, not only do the units change, the chemicals change. And if you don't set your goal, including the thing that you're solving for, like salt, you're going to be in trouble. So guys, grams, salt. Now we need a starting point. What do we know about the salt?
2.3.
2.3. You ready? This is sad. Moles of salt. That's the abbreviation for mole. That's sad.
1 or 2 mole. Well,
Drop the E. Mole.
We just write mole.
If you would prefer to include the E, that's just fine. Now, draw a line and a vertical line. Now, guys, this. We need to figure out how we can get from moles to grams. So, guys, turn your attention up in your notes as I bring this in. So we're going from moles to grams. But guys, we've got this conversion chart that helps us figure out the path. So we are going from moles to grams. So to get from moles to grams, what do we need to know?
formula.
The formula mass. Let's figure it out. Now guys, watch. You've already done this. It was the very first thing we did in class. But let me show you a shortcut to do this. Here's what you do. What is the mass of sodium chloride? 23.0. Guys, this is the way chemists do this. They just write the numbers up above the elements. So sodium is 23.0, chlorine is 35.5. When you add those up, we know that we get 58.5. But guys, watch my hands. Here's the deal. That's 58.5 grams is 1 mole. What goes on the bottom, the moles or the grams? Moles. So 1 mole goes on the bottom. What goes on the top? 58.5 grams. Now guys, watch. We cancel. Moles drop out with moles. We are left with grams. And then all we have to do is the math. So we've got 2.3 times 58.5. And guys, the answer is 134.55. But we're not done. What do we need to do? Significant digits. So guys, how many significant digits in 2.3? 2. How many significant digits in 58.5? 3. So we get 2, and this rounds to 130 grams. So guys, as accurately as we can tell, this weighs 130 grams. Again, guys, dimensional analysis just like before, but now we're leveraging this table. You okay? Let's do one more. Reads like this. How many molecules of water are in 25 grams of water? So guys, I forgot to grab this. Let me run next door and weigh this out. Okay. So guys, this is 25 grams of water. I just went and weighed it. So 25 grams of water. The question that we're figuring out is how many of these dudes are in here? You see where we're headed? Yeah. Okay. So guys, you pick your goal. You pick your starting point. You draw the line. You do the first 3 steps without me. Again, your goal goes on the right. Your starting point goes on the left. Spread them out. Draw a line. So guys, what did you put on the right? Particles, but let's be more specific. Particles of water or molecules of water, but you're right, that's particles. Now gang, what goes on the left? What do we know about the water? 25 grams. Then we draw a line, and then we draw a vertical line. And now guys, to put this in context, we are going from grams to molecules, which we know are particles. So now we look at our chart, and guys, where are we starting? On the right, on the middle, or on the left? We are starting on the right because we're starting in mass. Where is our goal? Left or middle? The left. But guys, notice the only way for us to get from the right to the left is we've got to go to moles first. So this is a 2-step conversion. We've got to go from mass to moles, and then we've got to go from moles to particles. So guys, how do we get from mass to moles? Formula mass. So guys, do this with me. Grab your periodic tables. To go from mass to moles, we need the formula mass. So guys, grab your periodic tables and look up the masses of these things. And let me reset this, and then we'll do this together. Okay, so guys, now what we need to do is we need to find these masses. So look up hydrogen. What is the mass of hydrogen? Right, but there's 2 of them, so what are we going to write down? 2.0. Stop. Guys, this is now wrong. Let me explain to you why. Guys, how many significant digits are in 2.0? 2. How many significant digits are in 25.0? 3. Here's the rule. This is brand new. Hear this. Guys, this number right here cannot have fewer significant digits than that number right there. So what that means is we've got to go back to the periodic table and we've got to get one more significant digit. So what is the mass of hydrogen to 3 significant digits? 1.01 times 2 is 2.02. So guys, the mass for hydrogen that we are going to use is 2.02. The rule is this: the masses that you get can't have fewer significant digits than your starting point, but will never go less than 1 decimal place. So now we need the mass of oxygen. What is it? 16.0. We're always going to go 1 decimal place. Do we need more? No, because that's 3 and this is 3. So now, guys, we add it up and we get 18.02. So what goes on the bottom? The 18.02 grams or the 1 mole? Grams. So 18.02 grams is 1 mole. Now our grams cancel and we're left with moles. But we're not done. Because, guys, moles puts us right here, but we now need to go to particles. So what is our conversion between moles and particles? Avogadro's number. So draw, oh gosh. Jeff, I blame you.
What?
Uh-huh.
You figured it.
Yeah. So guys, we draw a line, and now we know this. 1 mole is 602 septillion. So what goes on the bottom? The mole or the 602 septillion? Mole. So 1 mole of water is 602 septillion water molecules. Now we cancel. Moles drop with moles. We're left with molecules, so we're done. So now, guys, grab your calculators. If you don't know how to put numbers in scientific notation in your calculator, do not hit times 10. It's the exponent key, the EE button. If you don't know how that works, I'll work with you individually. But guys, we're going to go 25 divided by 18.2 times 6.02 times 10 to the 23rd. And when you're done with all of that, your calculator should say this: 8.35 times 10 to the 23rd. Some of your calculators may say 8.35 EE23. That EE means times 10. Don't write the EE.
I got 8.26.
Yeah, me too.
I got what you got. I got 8.25.
Hold on. Let me try it. 25 divided by 18.02
Oh, wait.
times 6.02.
They missed the divide by.
Okay.
Oh.
So guys, check again. Don't forget to divide by the 18.02. Are we now okay? Y'all okay? Now significant digits. So guys, looking at significant digits, how many significant digits are in 25.0? We've already established that that's 3. How many significant digits are in 18.02? 4. Now guys, watch this. How many significant digits are in Avogadro's number? It's just 3. All the other zeros that are trapped in this are non-significant. If you write it out, just like if you write it out, you would see that. So guys, this is actually just 3. Let me finish and then I'll chat. So guys, now looking at our limits, we've got 3 and we've got 4 and we've got 3. That means we're limited to 3. But guys, this number is 3 significant digits already, so we don't need to round it.
Why is it like a ton of decimals?
You can write them all out, but you're still going to end up rounding to 8.35.
Okay.
Go ahead, Jeff.
Isn't the mole to Avogadro's number perfect?
It is not. No. If you Google Avogadro's number, the most decimal places I've ever seen it out to is like 10. But it is not perfect. Yeah, so Avogadro's number at 6.02 is an approximation, and therefore it does limit significant digits. You guys good? Okay, so gang, this is how we're going to wrap up the day. Not bad, right?
These are always the funniest parts of your screencast because it's just like you saying
Quiet.
random stuff.
Me babbling.
The screencast can't do anything that we say.
You can like occasionally.
So guys, as you look over this paper, hopefully one thing, probably two things are going through your mind. Hopefully you're going to grab blank sheets of paper to work these on. If you're not, shame on you. But guys, the second thing that may be going through your mind is, please, please, please tell us we're only doing the odds. No. Guys, we are doing all of these. Here's why. There are so many different little twists and turns in these problems that if I were to assign you the odds or the evens, you'd be missing out on experiences that you're going to need. So guys, let's just say this. This is going to take you a little while, and I'm not apologizing for that. Typically in this class, you have no homework ranging towards 15 or 20 minutes. So guys, understand that when we unapologetically give you a homework assignment that might take you up to an hour, guys, the reason is not because we're trying to waste your time, it's because we're trying to help you be successful. So, guys, we will grade these on Friday. We will then do something on Friday that will be unlike anything you've done before. It's actually really fascinating. You're going to like it. But guys, when you get home and find that these are not as easy as I make them appear, please come and get help. And we now have the remainder of the day to get to work on these. So some of you are going, oh my gosh, I'm not quite sure what to do. Grab a paper, grab a sheet of paper, look at question number 1, write down your goal, write down your starting point, draw a line. Guys, reading question number 1. Question number 1 says, find the mass of 0.89 moles of CuCl2. What's your goal? Mass, write it down on the far right. Grams, CuCl2. What's your starting point? 0.89 moles, CuCl2. Then you're going to draw a horizontal line that stretches the width of your paper. Then, if you need, you can grab your notes page and you will find that you're starting in moles and you're converting to mass and looking at that conversion thing, just like here. Guys, looking at that conversion thing, you are going from you're going from moles to mass, which means that you're going to need the formula mass, and you just go from there. So guys, I got you started on number 1. When you're done with that, you got 21 more to go. The answers are at the front of the room. Let's get some work done.